All right, a couple of things that we're going to do in this video. We're going to talk about acids and bases, basically what they are, definitions of acids and bases. Then we'll look at reactions between acids and bases, which are called neutralization reactions. We'll write those reactions as net ionic equations. And then finally, we'll briefly look at a special case of acid-base reactions, which are the carbonates. They do something a little bit different, but carbonates are very common, so it's a useful thing to be aware of. All right, so first, acids. There are several definitions of both acids and bases, depending on the kind of chemistry that you're doing. One of the simplest definitions is the Arrhenius definition, named for Svante Arrhenius, who was a Swedish chemist a couple of hundred years ago. And the Arrhenius definition of an acid is a species that acts as a source of hydrogen ions. And this really should have been a superscript, so that should be H plus. Hydrogen ions in a chemical reaction. Okay. All right. There are two main groups of acids, strong acids and weak acids. We'll have a lot more to say about strong acids and weak acids in 1106. There's an entire chapter on acid-base chemistry. This is really just an introduction. But for now, we'll say strong acids are acids that are also strong electrolytes, which means that they dissociate completely in water, releasing hydrogen ions. Remember, we had this. I'm always using everyone. I always use hydrochloric acid. Basically, everyone uses hydrochloric acid. It's the stereotypical strong acid. So I'm going to mix it up and use hydrobromic acid. All right. So we discussed these in the last video when we were talking about strong electrolytes. But just as a review, that's an example of how a strong base behaves. It's a strong electrolyte, dissociates completely into ions, and one of those ions is H plus. In the last video, we also had a list of 7 common strong acids. Here they are again, so you should know these. You can think of them in 3 different groups. There's the hydrogen halides, okay, but importantly, not including hydrofluoric acid. And then there are 2 other common ones, nitric acid and sulfuric acid, that probably sound familiar to you. And then 2 that don't sound familiar. It looks like I missed another subscript there. Chloric acid and perchloric acid should be HCO3 subscript and HClO4 also subscript. All right, so hopefully you've already got those memorized from that last lecture video. All right, then we've got weak acids, and weak acids do the same thing. They release hydrogen ions in solution, but they are not strong electrolytes. So these are things like HF, which we said last time, breaks apart in solution to release ions. But the overwhelming majority of the molecules stay in this form. So very few of the molecules are dissociated, producing these hydrogen ions. Okay? Although if they're in a chemical reaction, they can still supply these hydrogen ions to the chemical reaction. So they still act as an acid, they just aren't strong electrolytes. Okay? And again, how do you know a weak acid? Weak acids are all of the acids that aren't on that list of strong acids. Again, that should be a subscript. All right. And bases. The Arrhenius definition for bases is very similar to that for acids. Okay, but these are things that dissolve in water and they act as a source of hydroxide ions. Hydroxide is the key to being a base in the Arrhenius definition. Okay. Examples are things like uh, sodium hydroxide, right, and potassium hydroxide. All right. All right. And just like with the acids, we have strong acids, or excuse me, we have strong bases and weak bases. And again, also just like the acids, the strong bases are things that are strong electrolytes. So these are things that dissociate completely in water to release hydrogen ions. These are all of the alkali metals, so sodium, potassium, lithium, rubidium, you don't see rubidium very often, and cesium. Okay, so all of the alkali metal hydroxides and most of the alkaline earth hydroxides, calcium, strontium, and barium. Notably, magnesium is not a strong base because it's not soluble, and beryllium hydroxide is actually not terribly basic. It doesn't really release hydrogen ions. Excuse me, it doesn't really release hydroxide ions. All right, so all of these strong bases are things that the alkali metal hydroxides and the alkaline earth hydroxides. Now, notice with the alkaline earths, because they have a charge of 2 plus instead of 1 plus, they're going to have 2 hydroxides. So when these act as a base, you get a plus 2 cation and 2 hydroxide ions. Okay. All right. And then, of course, there are also weak bases. Weak bases are things that are capable of furnishing a hydroxide ion, but they are not strong electrolytes. In 1106, again, when we talk about acids and bases in more depth, we'll have a broader definition of weak bases. But for now, I will say among the most common weak bases are the insoluble metal hydroxides. So the group 1 and many of the group 2s are soluble, they're strong electrolytes. Those are strong bases, things that are, let's say like cobalt 2 hydroxide, insoluble, that would be a weak base. Iron 3 hydroxide, insoluble, that would be a weak base. Okay. Again, these hydroxides are still available to react in an acid-base reaction, but it just doesn't, it's just not a strong electrolyte. It doesn't release them readily into the solution. All right, now neutralization reactions. Okay. If you have a reaction with an acid and a base, you always get the same sort of a general format for the reaction. Here is hydrochloric acid reacting with sodium hydroxide, and you can see we're producing sodium chloride and water. Okay. We're going to talk about this as a special kind of reaction, a neutralization reaction, but you might note also that this is really just a special case of a double displacement reaction, because what's happening is the cations and anions are switching partners. The sodium is going with the chloride and the hydrogen is going with the hydroxide. Because if you take a hydrogen and you connect it to a hydroxide, you get H2O, and that's what we have over there. Okay, so if you're trying to figure out the products, you can think of this as just a simple double displacement reaction, because essentially that really is what it is. All right, but for acid-base reactions, the pattern is always this. You have an acid reacts with a base, and that gives you a salt and water. Okay, so I'm just going to put a box around that first because this is important, and that's something that you should know. acid plus base gives you salt plus water. Okay. All right, but I want to talk a little bit about this term salt. Okay. If you go to the store and you buy salt, the salt is sodium chloride. And if you go into your kitchen or your pantry and you get a bunch of salt, the salt in your salt shakers, that's all sodium chloride. Okay. But in chemistry, salt is a general term which really just means a soluble ionic compound. So salt in chemistry terminology is a much more general term, and in this statement here, an acid plus a base gives you a salt plus water. We mean it in that general term. Okay, so the reaction between an acid and a base is always going to give you some kind of an inorganic compound, cation and anion together, right? That's this. That's the salt, and then the other product is going to be water. Okay. So, for example, let's say we had instead we had nitric acid with potassium hydroxide. Right? Then the salt would be whatever you get by grouping these cations and anions together. So you get potassium nitrate and again water from this hydrogen and that hydroxide. Okay. All right. Okay. So that's the general format for neutralization reactions. Let's take some of these and write them as net ionic equations because that's important. Let's take the one that we just did, hydrochloric acid plus sodium hydroxide. And we can start with a molecular equation. We already had this on the last slide, so this is simple. And I'm going to try, I tend to be a bit long-winded. You may have noticed that. I'm going to try to go through these pretty quickly because I know we did a bunch of net ionic equations in the previous video. In fact, if you want to pause the video now and jump ahead to the end, go ahead and work through this one, see what you can get, and then start the video back up again, and you can check my answers, and we'll go through it together with fairly minimal dialogue. I'll try to restrain myself. I just love talking about chemistry. Okay, go ahead and give it a shot, and then we'll compare results. All right, so for the total ionic equation, I just took these and broke them up. Of course, hydrochloric acid is a strong electrolyte, strong acid, strong electrolyte. So I broke that up into H plus and Cl minus. Sodium hydroxide is a strong base, so that's a strong electrolyte. I broke that up into sodium ions and hydroxide ions. Same thing with sodium chloride. It's a soluble inorganic compound, so that's a strong electrolyte. I broke that up. Water is a molecular compound, so this doesn't break up. And if you look over here, I kept that together as one species. All right. Then for the net ionic equation, of course, we want to go back and cancel out our spectators. Spectators here are chloride and sodium. And so our net ionic equation is H plus OH minus gives H2O. Okay. And you'll find, here's an interesting thing, when you're doing these net ionic equations, anytime you have a strong acid reacting with a strong base, if we think about it really hard, we might be able to come up with a couple of exceptions, but it's almost always going to be the case that this here is going to be soluble, and so the counter ions are always going to end up being spectators, and you always end up with the same net ionic equation for essentially any strong acid and any strong base. When you react them, you end up with that net ionic equation. So I'm not going to work through this here, but go ahead and try this. Try hydrobromic acid plus lithium hydroxide. See what your products are going to be. Write a molecular, a total ionic, and a net ionic equation, and see if at the end you don't end up in exactly the same spot. H plus OH minus gives you water. All right, let's try another one. All right. Now we've got HF plus lithium hydroxide. Okay. The rules are it's a neutralization reaction, so our product is still going to be a salt and water. So the salt in this case is going to be lithium fluoride and water. Okay. For the net ionic equation, this is where things get a little bit different because HF is a weak acid. It's not a strong electrolyte, and we're not going to break it apart. So when we go to our total ionic equation, this HF is going to stay together. So I'll write this as HF aqueous. Now lithium hydroxide, that's a strong electrolyte. So we can break that up. And then our product's lithium fluoride, that's soluble. So break that up into its ions. And water, again, water is a molecular compound, so it's going to stay together. All right. Then we'll cancel our spectators, and I think in this case we've only got one. Often our spectators disappear in pairs. Well, I guess they're still pairs because there's two lithiums, but we often cancel both a cation and an anion. In this case, the only spectator is the cation, lithium. So we get to our final result. Our net ionic equation is HF plus hydroxide ions give us fluoride ions and water. All right, let's try one now with a weak base instead of a weak acid. All right, so let's look at nitric acid with iron 3 hydroxide. Okay, that's basically rust, iron 3 hydroxide. It's not exactly the same as rust. It's essentially the same thing. We want the products. The products, of course, are going to be, we're just switching pairs, right? So we're going to end up with iron nitrate and water. We need to be careful with charges here because the nitrate has a -1 charge and the iron has a +3. So the formula for iron nitrate is FeNO3 3, and then water. All right. And now we also need to balance this because we've got 3 nitrates over here. So we're going to have to put a couple 3s in there. I think that does it. Okay. All right. I was using red because iron hydroxide is a red colored compound, but I'm not sure it shows up all that well, so I'll switch to another one. All right. Now for the total ionic equation. In fact, let's do the same thing we were doing before. Pause the video, work through to the end, and then I will catch up with you, show you my results. hopefully with minimal explanation, since I think you guys have got it by now. All right, so I'll see you on the other side. All right, so as I wrote my total ionic equation, I broke this apart because that's a strong electrolyte. Now, because there are three of them, there are 3 nitric acids, so that's going to give us 3 H pluses and 3 nitrates. Okay. Then we've got iron hydroxide here. This is a solid, means that it is a non-electrolyte. So I left that together. H doesn't look great. I left that together. Okay. On the other side over here, we've got iron nitrate. That's got 1 iron in it and 3 nitrates. Okay, so it breaks up like that. And then we've got 3 waters, so I've got 3 waters over here. Now we can go through and look for spectators. And I think our spectator, the only spectator we've got this time is the nitrate ion. So when we put all of that together, our net ionic equation is 3H plus iron hydroxide solid gives us dissolved iron 3 ions plus 3 waters. Okay. All right, so just briefly I want to talk about carbonates. Carbonates are fairly common. And carbonates do an interesting thing when you react them with an acid. I'll just put an ion here. I'm going to write this initially as a 2-step reaction, but ultimately you can think of this as 1 step. This is just kind of by way of explanation. Okay. What happens is when carbonates react with hydrogen ions, they form carbonic acid, and then carbonic acid itself is unstable. I guess unstable is a good enough word for it. So carbonic acid breaks apart into gas phase CO2 and water. So the net result is that anytime you have a carbonate salt and you react that with I should have 2 here, and you react that with hydrogens, ultimately the product is going to be CO2 and water, right? If you ever did that baking soda volcano as a kid, that's what this was. The baking soda has carbonates in it, and the vinegar is an acid. So when you react those 2 together, you get the CO2, and that's what makes the volcano fizz and appear to erupt. Okay. All right, so let's do one example of a reaction with a carbonate. All right, let's do calcium carbonate. It's limestone. And we'll react that with, let's do hydrobromic acid. We haven't used that very much. Okay. All right, so the, again, this is a metathesis reaction. So the cations and anions are going to switch places. Calcium is going to end up with the bromide. So you get calcium bromide as one of the products. And then the other product is going to be these hydrogens reacting with the carbonate. And so that's ultimately going to give you, as we saw just a minute ago, that's going to give you CO2 and water. Right. You get the same pattern anytime you react a carbonate. You're going to get some kind of a salt. As before, you're going to get CO2 and you're going to get water. Okay. And we can write total ionic and net ionic equations for this. The calcium carbonate is a solid, so we'll keep that together. The hydrobromic acid is a strong electrolyte, so that's going to split up. All right, calcium bromide is soluble. That's a strong electrolyte, so we'll split that up. And then both CO2 and water are molecular compounds, so we'll keep them as they are. All right, so this is our total ionic equation, and for the net ionic equation, we need to cancel out our spectators if we have any. It looks like bromide might be the only spectator in this particular reaction. So our net ionic equation is going to be calcium carbonate reacting with 2 hydrogen ions to give us soluble calcium ions and CO2 and water. Okay. All right, great. So just looking back over what we've done, we talked about acids and bases. We have definitions for them. As I mentioned, in the second semester, we'll have more definitions and some more intricate, some more subtle definitions. But a very good, simple definition for acids and bases are those Arrhenius definitions, where acids are those species that supply hydrogen ions, and bases are those that supply hydroxide ions. All right, we looked at neutralization reactions, and in all of these neutralization reactions, the pattern is always an acid plus a base gives you a salt and water. And remember, salt in this case is generic term for salt, meaning any kind of a ionic compound. Then we wrote net ionic equations for these. Again, we just followed the exact same rules that we used in the last video. Anything that's a strong electrolyte, break up into ions. Anything that is insoluble or is a non-electrolyte or a weak electrolyte, leave that together as a compound, right? Write that in its molecular form. And then finally, we looked at carbonates, and we said that anytime you have a reaction with a carbonate reacting with an acid, you're always going to get CO2 and water. Okay? And the rest of the balancing for that, we follow the same rules that we've always followed before. All right, terrific. That's it for this video. Thank you guys for sticking with me, and I look forward to seeing you in the next one.